Okay, so we are going to be proving two lines are parallel to each other. For those of you familiar with Superman, Bizarro Superman here, we're kind of going to be doing section 3.2, but backwards. So let's first take a look and just kind of remember the four theorems, well, three theorems and one postulate that we went over in 3.2. Just the basic ideas of them. Whoa. Okay, sorry, I had these out of order. So just to recap, these were kind of the theorems or postulates that we put together, the corresponding angles, alternate interior angles, those things. They basically said if you have two parallel lines and they are cut, intersected by a transversal, then these four things will be true. The corresponding angles will be congruent, the alternate interior angles will be congruent, the alternate exterior angles are going to be congruent, and the same side interior angles will be supplementary. I'm going to make a little sketch of this just to make sure we're all on the same page of what we're talking about. So we have two lines. Let's say they are parallel to each other, and we have a transversal. So the transversal is just going to intersect those two lines. We need to be able to identify which angles are which here. So I'm going to number some of these. 1, 2, 3, 4, 5, 6, 7, 8. Whenever these lines are parallel, we can assume these relationships. That's what chapter 3.2 was all about. We could set up equations, we could use one angle to figure out all the others, we could do all kinds of stuff with it based on these four relationships of these specific angles. So you'll need to be able to identify these, and we're still going to need to be able to identify these in the new stuff that we're doing. But in that section, we were working from this direction. We were assuming we had parallel lines cut by a transversal, and then we were saying, all right, since that's the case, we can do this stuff. What we're going to be doing in this chapter, or this section, is working this backwards. Instead of starting with parallel lines and showing this, we're going to be starting, or at least attempting to show it going the other way. We're going to say if we have corresponding angles are congruent, that means we have parallel lines. If we have alternate interior angles that are congruent, then we have parallel lines. If we have alternate exterior angles that are congruent, then we have parallel lines. It's all about showing that the lines that we have here are parallel in this chapter, based on relationships that we already know. And hopefully remember these, right? Corresponding means they're in the same position. So like 1 and 5, or 2 and 6, or 4 and 8. Alternate interior means they're in the interior between the parallel lines and on different sides of the transversal, 3 and 6, 4 and 5. Alternate exterior, same idea, but on the outside of the parallel lines, 1 and 8, 2 and 7, and then same side interior, 3, 5, 4, 6, right? So making sure that we can identify these by their appropriate name is important for this section too. All right. So here is our first, it's not a theorem, postulate. Postulate we have to accept to be true without proof. It's called the converse of the corresponding angles postulate. Hopefully we remember converse means that we take a conditional statement, in this case a theorem or a postulate they already knew, and we reverse it. So sorry, I went too far. I'm on the wrong page. I forgot because things were out of order. Let me fix this. Here we go. Converse of the corresponding angles postulate. I was talking about something that wasn't there. So hopefully we remember that converse means we take a conditional statement and we switch the hypothesis and the conclusion. We switch the direction that conditional statement is read. So the corresponding angles postulate states if we have parallel lines, then we have corresponding angles that are congruent. We're going to switch that. If the corresponding angles are congruent, then the lines are parallel. That's how we're going to show that two lines are parallel. This one is a postulate, so because of that, we have to accept it to be true without proof. But if we accept just this one, all of the others are provable based on this one. All of the other angle relationships will be true, and they will be theorems that are based on this one postulate. Again, the way that it works, If we can show corresponding angles that are congruent, then we can say we have parallel lines. It's actually pretty easy. It's not too complicated. And a lot of these parallel line proofs are going to follow a similar process. That's going to be different than the proofs we did in chapter 2, which were all kind of different. Some were about angles, some were about segments, some we had to write equations, some we had to create transitive property chains, all kinds of different stuff. These are all going to be relatively similar. It's all going to be about showing one of the 4 angle relationships: corresponding angles that are congruent, alternate interior angles that are congruent, alternate exterior angles that are congruent, or this one's the oddball, same side interior angles that are supplementary. If we can show any of those relationships, then we can say we have parallel lines. We're going to kind of go somewhat quickly through for the first 2 theorems, and then just kind of do an example of how we would write a proof. Sorry, remember, out of order. Okay, so our first theorem is the converse of the alternate interior angles theorem. So the alternate interior angles theorem states if you have parallel lines that are cut by a transversal, then the alternate interior angles are congruent. We're doing the converse. We're switching that. If the alternate interior angles are congruent, then the lines are parallel. Pretty simple. Again, it's all about showing the lines are parallel based on a known relationship. And again, we can prove this based on the postulate that we just talked about. I'm going to go ahead and click out of this and move forward in just a second. But again, the main idea here of this theorem says if we have 2 alternate interior angles and we can show that they're congruent to each other, that means that the lines will have to be parallel to one another. Okay, let me move on. I will post these notes. I don't remember if I posted them or not. I actually feel like I forgot to put them on our classroom page. I will put them on the classroom page for you guys to have at the end of class here. Oh, I'm jumping all over the place. Yeah, okay. So converse of the alternate exterior angles theorem. Same idea as interior, except we're dealing with exterior angles. So basically, if we can show that we have some alternate exterior angles like this here that are congruent, then we can say the lines are parallel. It's that easy. It's that simple. It's not too hard. If we can ever demonstrate we have alternate exterior angles that are congruent, then the lines are parallel. I'm going to clear this and I'm going to go ahead and look at the example proof. Again, I'll have these notes if you want to write some things down for you guys to look at after class. Okay, so let's actually look at what a proof of this is going to look like and think about it. So here is our drawing. We have some angles here. It is first given, that angle 1 and angle 2 are congruent. We can do this proof in 2 ways. There is an easy way. If we have already accepted the alternate exterior converse of the alternate exterior angles theorem to be true, then we can simply use that and say that these lines are parallel. It's extremely short. We can say, okay, angle 1 is congruent to angle 2. It's given. And then we can say L is parallel to M based on, I'm going to type this one out. Converse of the alternate exterior angles theorem. It's 2 steps. There's a given and there's a conclusion. That's it. If we didn't want to use this theorem, if we didn't want to use this one, and we wanted to instead use the corresponding angles one, we could do it that way too. So we could do the converse of the corresponding angles postulate. We could do this one as well, but it's going to require a few more steps. So I'm going to do it this way because otherwise it's sort of a trivial proof, right? It's almost done for us already. In this case, that means I need to show that I have some corresponding angles that are congruent. Based on this picture, the only corresponding angles I see are angle 3 and angle 2. So I need to somehow show that these are equal. Well, that's actually pretty easy because these here are vertical angles. Angle 1 and 3 are vertical angles, so we know they have to be congruent. And then because of these two congruent statements, we can create a chain. We can say angle 3 is congruent to 1 and angle 1 is congruent to 2. We can create a chain to say that angle 2 is actually congruent to angle 3 based on that transitive property chain that we just created. Transitive property of congruence. And now we have made use of the corresponding angles postulate instead. So by doing it this way, instead of the other way, we've actually turned this into a proof that shows why the converse of the alternate exterior angles theorem, we've actually shown that this theorem is valid. Because we've demonstrated we can assume if we have congruent alternate exterior angles theorem, if we have congruent alternate exterior angles based on the corresponding angles postulate, that means the angles have to be, or the lines have to be parallel to one another. So this could actually, the way that we wrote it this way can be thought of as a proof of this particular theorem. Since I didn't make use of it to prove it, and this is really a representation of that theorem anyway. It's kind of a weird concept. I'm okay with us using the short proof, like on a quiz or test or whatever. If we're doing one of these, you can go ahead and use this and make it a really short proof. That's fine too. All right, let's clear this and let's try one more example of this. See what it looks like. Thought that I had another one of these. Do I not? Okay. We will do an example in just 1 second. Last theorem, and this one is the one that's different because same side interior angles have a bit of a different relationship, right? They are supplementary. So we can use that relationship also to prove we have parallel lines. So if we have same side interior angles that are supplementary, that also means the lines are parallel. Now, this is a little more complicated of a relationship to demonstrate. There might be more steps involved in showing this rather than congruence. So that's why generally we'll probably use the other ones, but it's possible the only way we have is to do this. It just kind of depends on what the given information is and where we can get. Because this is more complicated. This involves actually setting up an equation, maybe making some substitutions in it, and then ending up with this. We'll see an example where we use this, but not right away. All right, let's do this one. The part that confuses students about this particular proof is we have two different sets of lines. We have lines L and M, which are actually given to be parallel. So I'm actually going to color those a little bit differently just to denote that these are special. These are parallel to each other. We can see it both in the given information here, that they're parallel, and also these markings mean parallel as well. So what that means is I can use all those theorems from 3.2. If I have parallel lines, then I know all four of those things. I know corresponding angles are congruent, alternate interior angles are congruent, alternate exterior angles are congruent. I can use all those theorems from 3.2 because I have parallel lines, which means I can connect angles that are in this grouping to angles that are in this grouping, again, because the lines are parallel. What I can't do is connect angles from a grouping up here to down here. because it is not given that these two lines are parallel. That is actually our goal. We are trying to show that. This is where people get confused in a proof like this. They don't know when they can assume to use corresponding angles or alternate interior angles and when they can't. If we have parallel lines, we can do it. If we don't have parallel lines, we can't do it. All right, let's see what this looks like. So we are trying to demonstrate that that line R and line P here and here are parallel. What it looks like based on my drawing, or based on the drawing here and what's marked for us, it looks like we're going to try to show these are congruent to one another. If we can show that angle 2 is congruent to angle 3, then I can say the lines are parallel by the, this is where it's long to write it out, but that's okay. It's the converse of the alternate exterior angles theorem. Because I'm just knowing where I'm getting to. This is an important aspect of a lot of proofs, is knowing where you're going to end and how you're going to end it. Obviously, we knew that we were going to end, well, I should have wrote this backwards, but that doesn't matter. If P is parallel to R, R is parallel to P, that's, I guess I should fix it, but minor difference there. They mean the same thing, right? Knowing where you're going to end up and how you're going to get there. That's an important thing to know about proofs. So in this case, I know I'm probably going to try to show that these are congruent and thus use the converse of the alternate exterior angles theorem, because these are alternate exterior angles, to say the lines are parallel. Now I need to figure out how I'm getting from the givens to there. So I need to see what is going to connect these things together. These are given. It's all about that middle section of a proof. How do we connect the given information, what we can see in the picture, down to our conclusion? So in this case, we have to make use of these two parallel lines. Since I know that angle 1 and 3 are congruent, and I want to show that angle 2 and 3 are congruent, I need to make a chain from angle 2 to angle 3. I need to be able to use the transitive property to state this. So what I can do, since these two lines are parallel, I can connect these. 1 and 2 are corresponding angles. Therefore, they have to be congruent, since L and M are parallel. So I can use the corresponding angles postulate to state that. I'm going to write the whole thing out. You could probably just tell me that they're corresponding angles. The only reason I'm allowed to say this, again, I keep reiterating this, but this is important, is because L and M are parallel. If I didn't know these were parallel, I could not connect that using this postulate. And likewise, I am not able to connect these because P and R are not parallel. All right, now we've created our chain, right? We have that angle 2 is congruent to 1, angle 1 is congruent to 3. So we created that chain between 2 and 3. So we are able to state this using the transitive property of congruence, and our proof's done. It's not that complicated here, but there's a lot of little things that it's hard and people get hung up on. This is a very similar formula that these types of proofs are going to take on. We'll do several more of these examples, but not right this second. Okay. Last one, and now this one's going to be the hardest one. So we're gonna take a little more time over it. We have about 9 minutes here. We're going to try to use the same side interior relationship. The reason this is harder is because that's a more complicated relationship. Same side interior angles are supplementary. So demonstrating supplementary is a little more complicated. We're going to have to set up an equation that shows two angles actually add up to 180. Let me go ahead and clear what I have. We'll go to that example. We'll come back to this in a minute. I don't actually want to do this one right now. It's a great proof. We will go over it here tomorrow. Okay. Let's look at our given information, kind of make some markings. Anytime you're doing a proof, this is important. Make sure you know everything that's given to you. So I can see here that angle 1 and 4 are congruent. So those are congruent. 3 and 4 are supplementary. So that's these right here. Since 3 and 4 are supplementary, that would allow us to say that M and N are parallel. That's not what we're trying to get to. We're trying to show that these are parallel. This would also let us set up an equation, right? Angle 3 and angle 4 being supplementary would let us set up an equation that measure of angle 3 plus measure of angle 4 equals 180. That might be useful. It might not. I don't know yet. I'm just trying to think about where we're trying to get. Okay. L and M are parallel. So these are these lines. When I look at a picture, they're usually labeled strategically. They're usually labeled with all of the things that I'm going to be making use of to try to write a proof. In this case, since between L and M, the only of the 4 angle relationships that I see are some same side interior angles, right? These are same side interior. I don't see any corresponding angles labeled, like one would correspond with this one and it's not labeled. So I'm probably not supposed to use corresponding angles. 2 and this angle here would be alternate interior. So there's no alternate interiors that are labeled. They exist, they're just not labeled. So I'm probably not meant to use that either. And again, I don't see any alternate exterior angles either. So it looks like I'm supposed to use same side interior angles to make this proof. I'm just kind of looking at what's labeled in terms of how the proof is telling me it wants to be done a little bit. They're always labeled a little bit strategically that way. So again, I'm going to start from the bottom, kind of fill in what we know, and then fill up the top and try to connect it. If you are more comfortable doing it another way, that's fine. So we are trying to show that L is parallel to M. And we suspect that we're going to be using the converse of the same side interior angles theorem. I'm abbreviating a little bit here. To do that, we're going to need to show that 1 and 2 are supplementary. So that's going to be that the measure of angle 1 plus the measure of angle 2 is equal to 180, right? That's what we need to show to state this, or at least that's one of the things we would need to show to state this. And our given was a few things. Angle 1 is congruent to angle 4, and 3 and angle 4 are supplementary. Typing it because I know there's a few more steps in this one versus the last one. These proofs in general are not long, but this one does have a few more steps. That was supposed to be congruent, right? So congruent. There are also some technical steps in this proof that I am not really going to do. When we know that 2 angles are congruent, that also means their measurements are equal, right? Angle 1 is congruent to angle 4. That means that the measurements are equal. A technical proof would state that as an additional step. I really don't need you to do so. All right, we did say we might make use of this idea. So I'm going to do this. Angle 3 plus measurement of angle 3 plus the measurement of angle 4 equals 180. That at least gives us an equation that is supplementary that we might make some substitutions for. And I actually already know that I can substitute angle 1 and angle 4 for each other. So I could already get rid of angle 4 in this if I want to. I'm not going to, but I could put angle 1 there. I do know that. Another thing that I see is these vertical angles. Again, I'm not 100% sure I'm going to use it, but it can't hurt to use this. So angle 2 is going to be equal to angle 3 because they are vertical angles. I forgot to put a reason here. What would be the reason that I could write this equation? That angle 3 plus angle 4 equals 180. Anybody in the chat?
Definition of supplementary angles.
And I keep spelling supplementary wrong. Okay. Yeah, since we know they're supplementary, we can set up that equation. All right, so here's what I'm seeing, and we have 3 minutes to close it out. So that's actually perfect, I think. Oh, let me undo that. No. Okay, we'll just live with it being yellow before I mess things up. I got a couple things that are going to allow me to make a substitution. These two things right here are going to let me substitute anytime I want, right? Angle 1 and angle 4 being congruent lets me substitute angle 1 for angle 4. Angle 2 and angle 3 being congruent lets me substitute for angle 3. So what I'm going to do is I'm going to take this equation and I'm going to make those substitutions. If I do that, if I replace angle 4 with angle 1, and I replace, so that's measurement angle 1, and I replace angle 3 with angle 2, I end up with this equation. It's pretty sloppily written, but the measurement of angle 2 plus the measurement of angle 1 equals 180. That's the same thing as this right here. And that's where I was trying to get to, right? So all I did to get that was use the substitution property. Since they were equal to each other, I can always make a substitution of one for the other anytime I want in an equation. Now, technically, the order of this was different, but the order of addition doesn't really matter. So I guess technically, because of the order here, I did also make use of something that's called the commute. We never learned about this in this class, but the commutative property of addition. The commutative property of addition basically states that I can add things. I cannot spell that word. That I can add things in any order. It doesn't matter. I can do 1 plus 2 or 2 plus 1. I'm going to get the same thing. That's something we know. But technically, I am making use of that to reorder it. But this would also be fine. Either way, I have shown that I have supplementary angles, therefore supplementary same side interior angles, therefore the lines are parallel, and we're good. And it's only a 5-step proof. It's a little more complicated than the other one because supplementary is a little more complicated of a relationship versus congruent. Okay, that'll end for what we're going to do right now. And we